All right, welcome everybody. Today we're going to talk about lesson number 96, which is actually our final lesson of the year. This is the second part of section 12.4, where we're specifically going to talk about limits of sequences. So you can see homework 96 there, and just a couple of things you might want to note. For 34 to 41, you're going to find the first 5 terms of the sequence, and then you're going to tell me the limit. That'll make more sense after we go through today's lesson, but just a little caution. The shortcuts and the rules for rational functions, those are great, but only when they work. If you see formulas, things that have the factorial or things that have the alternating sign, you can't actually use those shortcut rules, and you have to actually write them out and then analyze them before you can declare whether or not there's a limit. For number 46, ignore the directions that the book says, and all you're going to do is simplify the algebra and take the limit only, and then 48, follow the directions and do what it says. This is just, first of all, a quick reminder of the summary of what we learned yesterday, which is basically that limits at infinity follow the same rules as horizontal asymptotes of rational functions. And you're going to see that these rules actually have a direct application to sequences that we're going to look at today. So again, this is kind of the pre-calc explanation, the rules for horizontal asymptotes. You would, of course, compare the degree of the numerator and the denominator. If you were to have a larger degree in the numerator, then the limit would not exist, or the horizontal asymptote would not exist. If you were to have a larger degree in the denominator on the bottom, then the limit would be 0, or the horizontal asymptote would be 0. And of course, if you were to have the same degree on the top and bottom, then the horizontal asymptote would be at the coefficients, a over b, and the limit would exist there as well. So again, these are kind of the more straightforward rules, specifically for horizontal asymptotes. And then on this next slide, we kind of calculused it up a bit by kind of giving the formal definition using the limits. Technically, this slide and the previous slides say the same thing. It is important next year that you're able to kind of understand this more difficult notation, but I kind of wanted to present you with both for now. So today we're going to talk about limits of sequences. And again, it's very similar to the same properties of the limits as functions, because after all, a sequence is a function. You plug in some value and you get out some value. Instead of x and y, you typically use the variable n. So here we're considering the sequence a half, a fourth, an eighth, a 16th, a 32nd, and that is found by using the formula for the nth term, 1 over 2 to the n. So some of the stuff that we did back in chapter 9 was really kind of setting the scene for what we're going to talk about here. So 1 over 2 to the n. If you were to calculate the first 5 terms in that sequence, which is what you're going to be asked to do in a lot of the homework problems tonight, if you were to simply just look at these values, you would be able to see that the fractional percentage is going down. A fourth is less than a half, an eighth is less than a fourth, and so on and so forth. So just kind of using common sense, you could perhaps understand that the values are getting closer and closer to 0. If you think of it in terms of limits, okay, the numerator 1 is staying a constant 1. Where the denominator, 2 to the first, 2 to the 10th, 2 to the 100th, is just getting bigger and bigger and bigger. So if the top is remaining constant and the bottom is getting bigger and bigger, ultimately as you divide 1 by a larger and larger number, you're getting a smaller and smaller number, which is essentially 0. Again, this is only true if you are going to infinity, which all the problems today will, but it's just important that you're noticing that. And then a very, very, very important new vocab word. If the sequence is getting closer and closer to a number, we would say that the sequence is converging. So if the limit does exist, whether it's 0 or 5 or whatever, as long as all the values are getting closer and closer to some number, then we would say that the values are converging to that number. This here, again, is just the fancy way of saying what we just went over. Again, it is important that you're able to understand these more complicated calculus definitions, but it's also important, at least for now, that you just kind of understand the general idea. Again, this new word, converge. So if the values in the sequence are in fact getting closer and closer to some value, we say that the sequence is converging. If it does not get closer and closer to a number, we would say that the sequence is diverging. That means that it's not getting closer to anything. An easy example of that would be something like 1, -1, 1, -1. We saw a bunch of sequences like that back in chapter 9. Because the sequence will simply just go back and forth between those two values, it's not heading towards any one number, which means the limit does not exist, which means that the sequence diverges. So very important that you're able to use these words, and they mean the same thing mathematically that they mean in real life. Just a note here, okay? You've seen a lot of sequences that alternate sign, positive and negative. In this particular example, it's not the positive negative that means it diverges. It's the fact that there are two separate numbers that it bounces back and forth. It's possible that you could have some sequence that has a sign change that does converge. So don't get it twisted. Again, the change in sign does not necessarily mean divergent. You have to kind of look at the specific values in order to answer the question. So here is example 1. Find the limit of each sequence and assume that n equals 1 to start. So for the majority of the homework problems tonight, they are going to give you a formula for a sequence, and they're going to ask you to find the first 5 terms. So please make sure that you do that. I know that it might seem easy, but it's important that you remember everything about sequences back from chapter 9, so don't get it twisted. So if you wanted to find the first 5 values, you're assuming that n equals 1 to start. So you would plug in 1, you plug in 2, 3, 4, 5, or however many values they ask for. And then you're trying to find the limit of the sequence. So there's 2 ways to do that. If you're trying to find the limit of the sequence by just looking at the values, well, you can see here that from one fraction to the next, the numbers are getting larger. When you get here to 7/7, that's a value of 1. So you're getting bigger than 1. But if you were to continue finding terms in the sequence, the fraction will never, ever get bigger than a value of 2, which is why that's the limit. If you want to just kind of be able to answer that based on the equation, well, you're again going to follow those rules for rational functions. Consider the degrees. Because they're the same, 2/1 would have a limit of 2. So again, you can answer this question just by looking at it, but the homework does ask you to find terms in the sequence. So please make sure that you do that. It's important that you're able to make that connection. In B here, 2n plus 1 over n squared plus 4. Again, here are your values. If you were to calculate some of the terms in that sequence, you'll see that the fractional percentage is getting smaller and smaller and smaller. It won't ever be negative though. So if you're getting smaller and smaller and smaller, that is converging towards 0. Again, look at the degrees. Larger on the bottom means that the limit is 0. And finally, for C, if you go ahead and find a couple of values, and then you were to calculate those percentages, they are getting larger and larger, but they will never be larger than 1/2. How can you tell that? By looking at the equation. Well, again, take a look at your coefficients. Because they're the same, 2/4 simply converges to be 1/2. So it's important that you're able to marry what you're doing over here with what you're doing over here. So the majority of the problems in the homework tonight, 1, asks you to find the first 5 terms and then find the limit. And if you want to find the limit from the equation, that's fine, but just make sure that you're taking into account these terms as well. Then a quick reminder from chapter 9, these are the calculus summation formulas. You don't have to memorize them. You'll never have to memorize them. Basically, these were how you can quickly find the sum of I squared, I, and I to the third. So how does that kind of come into play with what we're doing here? Well, the only other thing you're going to be asked to do tonight is find the limit of a sequence that has this extremely messy formation here, which basically means this is some version of that calculus formula. Again, how did it get there? What does it mean? That's all what you're going to talk about next year. But for now, you simply have to be able to do the mechanics, the algebra. If you want to be able to easily tell me the limit of this sequence, you have to be able to simplify that algebra. So that's what you're going to do. Here is the equation. Notice that I multiplied the 6 times the n cubed and left that in the denominator. I put this 8 and this n together here. If you were to FOIL these 2 terms, and then if you were to distribute the 8n into that FOIL, and simplify, you would get down to this simplification. So again, All you really have to be able to do to set the scene for this, for next year, is you have to be able to do the algebra that's involved with going from the original problem into this simplified version. Once you have this simplified version, if I ask you for the limit, you can compare the degrees. You'll notice that they're the same, which means that the limit converges to 8/3.